In this section here, we're going to be talking about area. So if you followed the previous section on integration, and I think it was anti-differentiation, or I believe that's what it was, we're going to be talking about how to utilize that integration symbol by doing integration and finding area under a curve. We're going to start out with some basic stuff here, though, called sigma notation that you're going to need to know. But first, I'm going to go to the board and just kind of introduce you to what this next hour is going to be about. All right, so kind of in a nutshell here, let me draw up. I guess we'll use red for our axis, and let's just do a curve, and we'll just kind of arbitrarily on the screen here do a curve here. And the whole idea is what we're going to be wanting to do is find the area under this curve. So we're just going to be finding this area here, area under the curve. Now, if you've never found area, which I'm sure you probably have at some point in time in your life, let's use something else. Let's say I had a box. Now this is supposed to be a square box here. I'll do my best. And that means that this side is some x and this side is some y. And if we wanted to find the area of this box, well, the area is pretty easy. It's just equal to x times y. Or maybe you might see it as length times width. So that's to find the area of this box. But we notice up here in the top that the height of the box is not changing. As x increases, the height of the box is not changing. Therefore, we could simply just say x times y. But what happens when the height is changing? As x increases, the height, right? This height is changing, either getting increasing and then decreasing. So we can't just say, for example, this is y here, we'll go up to here, and of course here's x. We can't just say that y times x, or x times y, it doesn't matter, that this is going to be now the area of underneath of the what's underneath the curve here, that this is not the area. Of course, we could approximate it. It'd be a rough approximation, I guess. If you did this, you see this piece right here is getting cut out, this piece is getting cut out, and then of course we're adding some to this piece here. So we could do a box to kind of approximate this area under the curve. But what would be even better, and I guess we'll use blue for our XY axis now, it doesn't matter. What would be better is, so let's say we've got our curve here again. If we did smaller boxes, let's say. Okay, so I'm going to try to draw some boxes. But if we did smaller boxes, as you can see here, so let's say that we did smaller boxes. Now what that's going to do is that's going to reduce this error. So you see this little piece right here, that's these little pieces are getting smaller, but what we'd want to do here is we'd want to find the area of that box, we'll call that box 1, and then the area of that box, and we'll call that box 2, and then the area of this box, we'll call that box 3, and of course to find the area of all the boxes you just sum up the area of all of the boxes up to the nth box, right? And so that would end up reducing this error part right here, whereas up here we got, we got quite a bit of error. We got this piece here, and then of course what wasn't even underneath the curve. But that's basically where we're headed here. We're going to be summing up a bunch of boxes underneath the curve, and sum, the mathematical symbol for sum is this guy right here, okay? This is capital, this is sigma. And sigma means we're going to sum up a bunch of boxes here. But if we don't know how to use this, we need to probably look at that first. So that's what we're going to do.